Hello, I'm Ashley Arcidiacono from the Hansen Research Group at Florida State University. Today, I will briefly discuss our newest publication in the Journal of Physical Chemistry C, titled Examining the Influence of Bilayer Structure on Energy Transfer Molecular Photon Upconversion in Metal Ion Linked Multilayers. We're joined on this publication by Dr. Wei Yang from Florida State University and Dr. Scott Saavedra from the University of Arizona. Metal ion linked multilayers are a unique motif to spatially control and geometrically restrict molecules on a metal oxide surface, which is of interest in a number of applications, including flexible PN heterojunctions, stimuli-responsive drug delivery, as well as triplet-triplet annihilation upconversion dye-sensitized solar cells. Here we use a bilayer composed of a metal oxide surface, an anthracene TTAUC annihilator molecule, a zinc 2 linking ion, and porphyrin sensitizers with varying metal ion binding sites in the para, meta, and ortho positions as a means to probe the influence of these varying positions on things like energy transfer, photon upconversion, and photocurrent generation in the bilayer. Looking at ground state electronics, we observe that all of the porphyrins, both in solution and on the surface, behave similarly. However, when incorporated into the anthracene porphyrin bilayer, we can see large changes in both the forward energy transfer, TET, from the porphyrin to the anthracene molecule, as well as differences in the back energy transfer, ET, from the anthracene to the porphyrin molecule. It is likely that these differences are orientation related. Additionally, binding group position affected upconverted photocurrent, and thus the ith value of each system. We observe that the second order rate constant of TTA, however, remains the same for all bilayers, suggesting that the second layer molecule does not interfere with triplet exciton diffusion and can thus be independently tuned in the future to maximize second layer performance without affecting the first layer. From polarized attenuated total reflectance measurements of the bilayers on ITO, we found that the orientation of the first layer, those anthracene molecules, is largely unperturbed by subsequent layers. This accounts for those similarities we previously saw in the gamma TTA value. However, the tilt angle of the porphyrin plane can vary dramatically all the way from 41 to 64 to 57 degrees, which is likely responsible for the variation in the energy transfer rates that we previously observed. We go on to show, using molecular dynamic simulations, that there's considerable flexibility in the porphyrin orientation. We also observe that the bilayer structure does indeed impose an orientation on these molecules, seeing as the kappa squared value favored is threefold larger than that assumed for typically free rotating molecules. Perhaps most importantly, we find that the average structure is an insufficient way to predict the ensemble behavior, because even the smallest subset of the population with highly favorable energy transfer rates can be the primary driver, thus increasing the likelihood of energy transfer. Overall, gaining control of the orientation and its distributions will be a critical step in maximizing the potential of these metal ion linked structures. If you want to learn more about the publication, please visit it using the DOI at the bottom of your screen, and feel free to follow the Hansen Research Group on both Instagram and Twitter. Thank you so much for your time today.